Okay, line A6, learning task 3, we're going to talk about SCR operations. And it's at the very first part of this learning task to give you a mechanical analogy of what an SCR kind of operates like. And an SCR is something that's going to allow flow, and whenever there's going to go and be flow, it's just going to be triggered by a very small action. The analogy they use over here is that there's going to be a small latch pin. We've got a gate that's got a spring that is going to go and hold this gate, closed more or less. Once we pull this latch pin, provided that there is stacked up force behind this gate, that gate will then swing open like that. I don't know what they did on the drawing here on this side, but the gate should swing open to the side like that over here, and then the spring is being held taut. But the flow of whatever sort of water they have through it, continues, and as long as there's enough water flowing through this sluice, it's going to go and keep that gate pinned up against the far wall. As soon as the flow would start to go and drop off, though, we're going to go and lose that ability to keep the gate pinned, and then the spring would be able to go and once again pull that gate back past this little latch over here. That's the analogy that they use. I like the analogy of holding a door open. Really, if you get one person to kind of open the door, if there's a door and you have a bunch of people that just kind of walk up against the door, they're going to get stuck. But as soon as one person, turns that handle, it's a very small action, then everybody else can continue to go and bump through that door. And as soon as the last person goes through, the door closer closes that door behind them again. That's really what the SCR is going to be. It's going to be a controllable thing that is going to maintain conduction or flow through it, provided that there is a sufficient amount of flow through it. Let's take a look at the actual electrical characteristics of it. First thing we're going to take a look at is we're going to take a look at a good side and a bad side to our diagram. What we have over here, this is going to be bad operational side. This over here is going to be my good operational side. We're going to go and break it down from one to the other. Over here, I've got reverse current. Over here, I've got forward current or conduction current. Over here, I'm going to go and have forward voltage. And over here, I would have reverse voltage. A couple of different ways that we can turn these on now. From the previous learning task, you should remember that there was this thing that we refer to as being the dV/dt. Or the delta V, delta T. Sometimes it'll be a dV dt as well. But what this means is rate of change. In other words, if we have a fast enough rate of change that is going to go and happen in our circuit where this variable voltage supply over here just whoosh swings on really, really suddenly, we can trigger these things into conduction. That's one of the ways that we can go and reach this. It's called our forward breakover voltage if we just reach the value that it's going to turn on, or it's going to be our forward. It's a ratio, this dV/dt. They would call this the steepness of the leading edge, the change in voltage over top of the change in time. If we have got a really, really steep change in voltage over a relatively short amount of time, we're going to kick it into conduction. Alternatively, we could also just go and exceed the voltage ratings of this. If I go and bring this to a really, really high value of voltage, we're going to be able to break this thing down. We're going to be able to run right over it. And if I do that in a reverse direction, I'm going to be able to go and do the same thing. I can go and stick a reverse value of voltage, and then I'm going to go and have a reverse value of current. There'll be a small leakage value of current that's going to happen because the semiconductor is still a complete path the whole time until I reach this point where I get a reverse avalanche breakdown voltage. And at that point, the thing is broken down in reverse, and my reverse current, that's everything going down like this, is going to go and take off, irrevocably, destroying this thing. On the forward side over here, just erase all that, if we go and increase our value of voltage either really suddenly or if we trigger this thing into conduction, what we are going to go and get is we are going to go and get forward conduction. So anytime that we start applying a forward value of voltage, we see that we start to get a small forward value of current. And this is just due to the fact that these are solid blocks. There's no gap in here. It's P material, N material, etc. There's always going to be some imperfections and some leakage current. But then if we get to a value where we all of a sudden turn this thing on, so we're going to trigger that gate circuit, that's this gate over here, then all of a sudden, once we trigger that, we are going to go and start getting on forward value of currents. They split the graph up actually into two separate things. This one over here, this lower line that I'm going over top, I'll just highlight that one. This one is just what shows what it would be like if I don't use the gate. It would show that I'm going to go and get a small increasing amount of current as this thing goes along with a increasing amount of voltage. So as the voltage goes up, the current goes up slowly, and then all of a sudden I would reach a point over here where this thing would go and turn on, and then I would be able to go and carry load of current through. Not the proper way to go and turn it on. Proper way to turn it on is to go and increase our value of voltage, and then we're going to hit that gate. And once we hit that gate, we then can go and get a large amount of current that's going to go through. The more voltage we put through here, the more current that we are going to be able to go and drive through. This is the proper way to go and do this. Now, we are also going to go and have what we refer to as our I holding. And our I holding is going to be the amount of current that we need to maintain conduction. If our current drops, so if this current level would start to go and drop back down and it gets below our holding current value, then all of a sudden it's going to go and shut off the SCR. And the SCR is going to go back into this yellow region over here where it's just acting as if it were a blocking chunk of semiconductor. Ultimately, what our SCR does is it acts the same as if we had a diode in series with a switch. You should remember diodes. There was a little review at the beginning of this, but a diode is going to be a one-way component that's going to only send current through in a single direction. A switch is something that's going to go and establish or cut off current flow. So we'll just call this thing on-off control for that. All of these things, one-way direction for current and the on-off control, are all placed inside of one device when we go and create an SCR. And we've got the anode, the cathode, which are going to be the same as what we have on the diode. Anode being this end here, which is going to be my positive end, and then my cathode being this end, which is going to be my negative, and then this, which is not G for ground, but it is G for gate, which is where I'm going to go and place a very small value of voltage in reference to the cathode, a small positive value of voltage to go and kick this thing into conduction. What we need to do is we do have to bias it properly inside of a circuit, and biasing the main body of it, we're just going to go and ignore all of this here right now. What I'm going to do is I'm going to start by biasing the main body, and the main body gets biased by taking our supply over here. So you get a positive and a negative. I'm going to place the positive to this end, which is the anode end. I'm going to place the negative to this end, the cathode end. I'm going to have a load in there because remember, this is just a semiconductor or a solid-state switching device. I don't want to place this thing directly across from here, right back to there, because then as soon as it was turned on, we'd have a short circuit. We're going to go and use these SCRs to control some sort of a load that's going to be associated with it. Once we've got the main body, the main current carrying channel placed in there, the next thing we're going to do is we're going to have to go and put on a gate. And the gate is going to be a control that needs to be a slight bit more positive than what I've got over here on this end, which is going to go and be my cathode. So the gate needs to be brought to a slight bit more positive. Over here you can see that they're doing it with a separate DC supply. It's allowable. I could tie my separate DC supply onto here and have a small positive value of voltage that I would use to turn this thing on. Or in a lot of cases, you're going to go and take it directly from the main over here as well. What would I need to go and create conduction inside of here? Well, all I would need to do is I would need to go and depress this button. As soon as I do that, I would get a complete path for current through here, which would go and give me a little burst of current. It's going to go and drop that first depletion region at PN junction. And now I'm going to be able to carry my bulk current, the actual load current, through my circuit over here. I only need to keep this closed for just a brief instant. As soon as I go and open this thing up, it is going to go and maintain conduction, provided that my value of current here is larger than my holding current value that I need to go and have. So I'll continue to go and have current that's going to go and travel through here. If I want this thing to go and shut off, I have got no way to go and shut it off other than to drop the current itself. So I might have a variable resistance over here, or I might have to go and have another separate switch in line with it that would go and shut this thing off. Both of these are going to go and be impractical. The whole point of the SCR is that we can turn it on and we want this thing to be able to go and turn off as well. But remember that it's got the dual characteristic of having both one-way directional as well as having a switching. It's an on-off type of thing. What would be lovely is if we had some sort of a current flow that would shut off by itself. Well, we do have a current flow that would shut off by itself, and that's going to be when we place this thing into an AC circuit. But right now, while it's inside of a DC circuit, we have no way to shut it off unless we interrupt this cathode cathode to anode current, or my main channel current, some way. Either change the resistance on this, increase the amount of resistance, drop the current till it falls below the holding value, or open a switch inside of here. And they demonstrate that inside of your figure number 5. If I placed it into an AC circuit, we all of a sudden have this wonderful thing where we are going to be able to shut off the current automatically because our AC current does that. AC starts, builds up, hits 0, builds up in the opposite direction, hits 0, builds up in the opposite direction. Anytime that my voltage is equal to 0, therefore also my current would have to be equal to 0 no matter what the value of resistance is, which means that guaranteed anytime that I cross this line, that's something that's called commutating. You should remember that from your AC theory at the beginning of second year. Anytime that I go into commutation, I'm going to go and drop below holding current and it will automatically shut itself off. So here we have a simple circuit that is now going to be inside of AC. First of all, I'm going to go and remove the SCR controller. We're going to look at this thing as if it were just a diode. If this was just a diode, we would know that the diode only conducts anytime that my anode is positive and my cathode is going to go and be negative. So anytime that my AC is positive here and negative here, we would have conduction through here. Current would be able to travel through the resistive path and all the way back up. But remember that AC does flip, which means that all of these values over here are going to go and flip. This side will now become positive. This side will become negative. All of this happens 60 times a second. We go positive, negative, positive, negative. And as soon as I get a negative over here, we would see that the diode would be blocking. So it would block this waveform right now when I've got a negative positive over here, but it would have passed that waveform whenever I've got the positive, negative. That's going to look like that. Our SCR is going to do the same thing. It's only going to go and pass stuff when we have got the proper polarity on the main part. So I take a look at my anode and my cathode, and when I do, I see that I've got them forward biased. Anytime that I've got positive, negative here, this thing is going to be able to go and turn on. And as long as I would then go and hit this little circuit over here, and I know this really bothers some of you, the fact that we've got AC circuit over here and that we've got a DC circuit over here, but you're actually allowed to go and combine circuits because where does current want to return to? It wants to return to its source. So we'll have two separate paths of current right now. The AC current will be this blue current over here. It's returning back to the transformer where those magnetic fields have been ripping the electrons from their orbitals and pushing them around. This is where its current wants to return back to. On my other one, on the actual little DC circuit over here, I'm going to go and have DC current that is just going to go and travel through here. This DC current, represented here by the red, has got zero interest in going anywhere inside of the AC circuit. Same as the AC circuit has got zero interest in going anywhere inside of this DC circuit. They both just share this one little line where they're going through, and all that's going to do is it's going to give us what we refer to as a DC offset to that AC value. Okay. Going back into this, if I go and give this thing a closure, we are going to go and have DC applied to this, which is going to go and break down that very first depletion region. It's going to allow us to pass current, which would allow us then to go and pass current from the AC source anytime that it's looking like this. But anytime that my AC source reverses, and I go to negative here and positive over here, then this thing is going to be blocking. Even if I've got the gate signal applied, it is still going to be blocking the AC flow. And ultimately what we end up with is we end up with a current that is going to go and look like this. And a voltage that's going to look like this and a corresponding current that's going to look like this as well. Where we are going to only see half of that waveform and the other half, which should be there, is just cut away. It's blocked off by the way that our thyristor just cuts off current. It's a one direction type of device. So we lose that whole bottom half and we're only left with the top half over there. That would be what it would look like for single phase rectification if I were to go and leave this whole thing, if I were to go and leave this push button right over here on all the time. I'm not going to leave that on all the time because we only need to give it a little push, and any extra current that we're running through there is really just going to be seen as being a loss to my system itself. What I'm going to do is I'm going to go and give myself a gate control type of circuit. And that gate control circuit is then just going to be a timed operation. You're going to want to go and coordinate it with your AC supply over here, and you're going to go and have your current that will then be able to travel through in this direction only, because it's a one-way device, through my SCR and to my load. And this is going to go and just choose the amount of time that I'm going to go and have that waveform applied. Time is almost equally as important as the actual magnitude of something. I want you to all just think to something really, really hot. Okay, so you've been using your unibit. You've been drilling holes in electrical strut for the last half hour with that thing. If you touch that unibit, what's going to happen? Well, everybody knows you're going to go and get burnt because that thing is hot. But if you touch it really, really quickly, even though that unibit is still at its full temperature, you're not going to get burnt because you only had a short amount of contact. And so the overall net effect is going to be much lower on you. The bit is still just as hot as it was, but because your time that you spent in contact with it was small, you don't get much of an effect from it. Whereas if you stick your hand around that thing and you just grit your teeth and hold on to it, you're going to end up with some massive third-degree burns off of that. We don't want any of that, but we're going to get the same type of a operation inside of my electrical circuits. If you take a look at the bottom over here, what we see is we're just seeing an amount of time that we're allowing that waveform to go and be present. If we allow that waveform to be present, the entire waveform all the way through, we're going to go and get a lot of power that we can pass through my SCR over to my load. My load is going to go and receive and dissipate a lot of power. But if I chop away part of that, if I wait a little bit before I turn this thing on, I'm going to have less power because there's less time that's got the waveform applied. And if I wait a bit more and chop away a bit more of the waveform before I turn this thing on, then I'm going to have less power. And I can go and chop it away till I have even less power or all the way down to zero power. It's still the same waveform for all of these that's going to be there. It's just how much of that waveform we are allowing to go and pass through with this SCR. This is what is going to go and give us phase control. And phase control is going to be defined into two distinct periods of time. We are going to go and have our conduction, and we are going to go and have our commutation. First of all, because it is a one-way device, each SCR is only going to go and see half of a cycle. And half of a cycle is going to be called a alternation. Alternation. You could draw a little cowboy hat, what an alternation. Anyways, this is a alternation that we have here for this, and that alternation is broken down into two sections. One of them is going to be your firing angle, the other one is going to go and be your conduction angle. Firing angle always happens at the beginning of it. You're never going to see a firing angle at the end. You can never cut away the back part of it. You can only cut away the front part of it. You're going to wait, and then boom, when you turn this thing on, all of a sudden it's going to go and put the rest of the waveform over top of whatever your load is. And then as that voltage drops away, your current is going to go and drop as well. I is equal to E over top of R. So as your voltage goes down, your current will go down as well. So as your voltage drops away, you're going to hit a point where your voltage level is going to be low enough that it is no longer going to be able to go and have a sufficient amount of current, and we are going to go and fall below the IH, or the holding current value that we are going to go and have. We're going to define these things angularly, or the amount of angles that it is going to go and transmit for. Because an alternation is half of a cycle, an alternation is equal to 180 degrees. And so out of that 180 degrees, we are going to go and cut away only part of that 180 degrees. There is a formula for this one. Formula is given inside of your binders there. It should be on your page 31. And the formula is one that involves a few of your trigonometric operators over here. What we need to do is we need to go and say that the amount of voltage, the effective voltage we're going to go and have through, is going to be the E peak. So E peak is what we would normally go and have for this thing, multiplied by 1 plus, I'm running out of space, so just erase that, 1 plus cos alpha. That's the Greek letter alpha over there, all divided by my 2 pi. And this 2 pi thing is indicative of the fact that this is in radians, or the amount of the circle that this thing is going to go and be part of. We talked about it really briefly just at the beginning of AC, that there's 2 ways to define circular things, or 360 degree things. A phase, a cycle, is going to be 360 degrees. One of the ways is to go and use degrees. The other one is to go and use radians. And radians always work around 2 pi because an entire circle is equal to 2 pi radians that we are going to go and have. Anyways, this formula over here, what you're going to get out of it is you're going to get an average DC voltage. It's going to be a pulsating DC voltage that is going to, oops, sorry, it shouldn't just be like that. It should be a hump and a line, etc. As this thing goes across. And it's going to be, then starting to chop away at those humps. Less of a hump and then a line, less of a hump and then a line, etc. as we go along there. And it's going to give us an average value of DC voltage. In order to calculate that, though, we do need to know this value over here, what my peak value of voltage is going to go and be from this thing. And I need to know what my firing angle is going to go and be. That's going to be this alpha that we are going to go and have here. A for alpha, A for angle over there. They give you an example calculation for an AC value of 120 volts, but then they use an E peak of 170 volts. You should remember from your simple AC theory that if we are looking at peak values of voltage compared to our RMS values of voltage, we usually deal with RMS, but our peak is going to go and be 1.414 or 0.707 divided out of it, greater than that. So you would just go and take to move from a value of 120, you divide by 0.707, which will bring you up, we'll just do that, 20 divided by 0.707, which gets you to 169.73 or 170 volts, which is going to be the peak of your 120 volt system. Full wave rectification can also go and happen. What we've looked at so far has been half wave rectification. It's been a half wave controlled rectification where if we were at full power, we would get this full waveform out on each of these, but we were always losing this half over here. We can go and get full wave rectification out if we go and use back-to-back type of circuits. Two different ways that we can go and do this. One of these would be to go and use what we call a biphase center tap transformer, where we're going to go and alternate which one of these two ones will be forward biased at any given point. We know that AC changes around its bias, so if my AC is positive here, therefore this point must be negative, right? And we cannot have, light without dark, we can't have positive without negative, etc. If this point is negative, disregarding the top over here, this point over here must be a slight bit more positive in relation to it. And in relation to this positive over here, this point must be a slight bit more negative over here. So we've got this point that's got a positive thing kind of going on over there. Because it really depends. It's all a point of reference. Whether you're looking towards here, you'd see that as being more positive, but if you're looking towards here, you see it as being more negative. Right now, with my AC like this, I take a look at both of my SCRs and I say, which SCR is forward biased? Well, this one's got a negative applied to the anode, therefore this one would be blocking. But this one over here has got a positive applied, and I can apply the negative through there, so this one would be forward biased. So during this cycle, right now, I would be able to go and send current through here. If I trigger that, I'll be able to send a loop of current through over there. Remember though, because I've got AC, now my AC is going to go and alternate, which would mean that now this positive is going to go and become a negative, and this negative becomes a positive, drawn blue for the second half. If I take a look at this being a positive over here, then this point would have to be a slight bit more negative in comparison to that positive. And if this point is negative, this point would be seen as being a slight bit more positive in relation to that. Once again, I just take a look at these and I compare them to the SCRs. I see I got a negative now attached to a anode, which would mean that this is going to be blocking during that cycle. I've got a positive attached to anode, which would mean that this would be forward biased during this cycle. And so I would go and have blue current over here that would be able to go and flow through at that point. And so what we're going to see is we're going to see this alternation between each of these two. We're going to go and, if I take a look at this, both of these drive their current through the load in the same direction. And so really, if I wanted to go and take a look at it, I could say that I'm going to go and have red current, and I'm going to go and have blue current, and my actual load just sees, it's going to see a bit of red current, then it's going to see blue current, then it's going to see red current, then it's going to see blue current, and the amount of current that travels through is all going to be defined by my trigger pulse, or what I'm going to go and have for a firing angle. If it's a tiny firing angle, that means we're not cutting away a lot, which means we're going to be putting a lot through that thing. This is one way to do it. Now, it is not always our most efficient because it does require the use of a transformer, and transformers are made out of copper, and the whole point of semiconductors is that they're not made out of copper, which means that they are cheap comparatively. What we oftentimes will prefer to do is we will go and prefer to do this methodology, and this methodology can be drawn in a number of different ways. You've seen bridge rectifiers before. You've seen them possibly also drawn as what they refer to as an H bridge over there as well. We're going to leave them inside of this configuration over here, but there is another way that you can draw them. I'll just quickly draw that one out over here, and that is going to be, if I have my AC, just stick 2 lines across the top over there, and then I'm going to stick my load right here in the center. Load right here in the center. Fundamentally, it's the same as this. It's just a different way of drawing this one through. And then I'm going to go and have that. And then I'm going to go and have a corresponding one like that. And then for the opposite side over here, I'm going to go and have this. And then I'm going to go and have, let's do that one in the wrong direction there. This, like that. And really what this one would allow me to do is this would, right now I'm just drawing only the diodes, but if I have got a positive, negative, I would see that this one would be conducting, it's going to be positive. This one would be blocking, because I've got a negative applied to there. This one would be conducting, because I've got a negative applied to there. So I would see that during this, the red cycle, I would be able to travel up, through in that direction, and back out. And then if I were to go and change this thing over to the other alternation, positive, negative, like that, I would see that I would have this one. That would be conducting, and this one. That would be conducting, negative to the cathode, positive to the anode. And so I would once again go and have current that would go and travel through, and back up, like that. So I take a look, this current, negative, would travel through like that, going from my negative over to my positive. This red current would go through from here, up and through, out like that, and so I would see that I would get the same direction. So what we have over here is the H bridge, or the just bridge rectifier circuit, can be drawn like that. All that they've done right now is they've added in an SCR, a single SCR, that they have placed in right over here. And then they're going to go and gate that SCR with a little control circuit so that they can control whatever current goes through. Same thing as up top here as what we have down here. Just another way that you're going to see these things drawn that you should be familiar with, commonly just referred to as being an H bridge, where you draw the load in the middle. These over here are going to go and provide for me rectification. That's all that these 4 are going to do, is we're going to go and use just power diodes to provide full rectification, full wave bridge rectification. And then we're going to use the SCR to take that rectified value of voltage and just chop it away every time. Chop it away, chop it away. Which ones of these are going to go and be my positive and negative? Well, I'm just going to take a look at this. I'm going to see that if this is positive right now, I'm going to take a look at which one passes. Will the positive pass to the cathode? Absolutely not. Will the positive pass to the anode? Absolutely. So this top bar over here must be my positive. And then if I go and change that now to a negative, I'll take a look. Will a negative pass through there? Nope. Would a negative pass through here? Yep. Therefore, the bottom would be my negative of this. So looking at this, I can say that this is what my rectified voltage will be, pulsating positive here with a negative over here. And then I'm just going to go and line my SCR up with that. See how my SCR, the anode is attached to the positive and the cathode is attached to the negative like that. And then I just have a control circuit that would just control how much we're cutting away, and the remainder gets to go through that DC load and power that DC load up. This is simpler in the fact that we use easy to come by power rectifier diodes, but we're able to go and control all of that current then just through the single SCR that we have off of there. Gives us a really good way to go and control the total amount of power that we're going to see out on our load. Once again, by the amount of time that we allow that power waveform to be there is going to determine how much apparent power the actual load itself is going to go and see. More contact with the voltage means more output of power. Going back down to testing now, you can go and ohmmeter test your SCRs. If you are going to go and ohmmeter test your SCRs, you need to first start by figuring out which of your Ohmmeter leads as positive and negative. Inside of every meter, there's always going to be a battery. That little battery is going to provide currents that is going to go and run your little tiny bit of current out anytime that you're taking resistance. So you always have to be using these things with a measurement of resistance there so that you have that turned into it. What you can do is you can go and verify which one of these is going to be positive and which one of these is going to be negative. Really? We just go off of which one of these is red and which one of these is going to go and be black. Quite honestly, that is going to always determine which one of these is going to be positive and negative. We do use the red and the black jacks on our meters for some stuff. The black jacks on there, I want you to just think about wearing black shoes. That's where you're standing. The red is where you are always looking over. Think about like red laser eyeballs. That's what our meters have, but it's actually where we're standing is where we're sending current out, through, etc. back down into it. So to test the SCR, first you have to know which is the positive and negative on your meter. All of this thing about verifying ohmmeter polarity, don't worry about it because just use the red and the black off of it. Now, how do we actually make it operate on a meter? Well, the meter itself, what we'll do then is we're going to take the negative or the black lead of our meter. We will connect that over to our cathode. The red lead of our meter, we are going to go and connect that over to our anode. And then all we need to do is just tap the gate lead to this. And when we do so, it is going to go and bring the gate a bit more positive than the cathode itself, which is going to go and put this thing into conduction. Now, I should warn you that it's not necessarily going to go and work because a lot of your meters don't put out a ton of current because they're not designed for that. You know, we're not trying to power stuff up and we really want our batteries to last. Everybody gets pissy when they have to buy another $3 battery. So we don't have a lot of current that we're going to usually deliver out of our meters. It's not going to work with all meters, but it is a method that you can use to go and test them. Quite honestly, I would probably put them directly across a battery myself and put an ammeter in line with it rather than going and doing this thing where they're trying to run it off the meter itself, because chances are your meter is not going to go and do it. They give you a little warning at the very end of their steps there to go and say, hey, you know, your ohmmeter has to be able to supply sufficient gate current to trigger it and to go and run it. In a lot of cases, if that's not going to go and work, your best bet is to go and just take a single cell. Let's draw one up over here. We've got our actual SCR over here. What I can do with that SCR is I can take that SCR and I'm just going to attach it to like a single C cell or a D cell or something like that. You can put a little resistance in line with it. I'm just going to go and run it all the way around the outside of this just because I need room for the drawing over here. We'll put a resistor in line with it just so we don't have a crazy amount of current. And then I'm just going to go and stick my ammeter. Okay, I'm just going to hook it onto my two leads of my meter, the red and the black, so that I am connected to the ammeter. This is my red lead. This is going to be my black lead. And I'm going to use my meter as the ammeter. Rather than trying to deliver the current out of the meter, which isn't going to work, I'm going to go and deliver it out of just a C-cell battery. And then all you need to do is you just go and take your gate lead, and because your gate lead needs to be a bit more positive, you can go and just quickly tap it to whatever you've got for your positive lead over here. Tap it to that, and you should see current passing through this thing. At that point, you're lifted up off of that. If your current is high enough, depending upon the value of your resistance, if the current is high enough, then it is going to go and continue to go and run through here. Generally speaking, as you get, if you get into industrial electronics in particular, you should have a couple of fairly high wattage rheostats, variable resistors that are going to be with you so that you can actually do this testing on the fly. You'll just take that and you can go and once you establish that current, so you do that tap, turn this thing on, you got current through there, and then what you can do is you can go and increase your resistance. As you increase your resistance, bring it across this thing. Sorry, wrong direction. I would have to go and bring it this direction. As I increase my resistance, I'm going to drop my amount of current, which eventually should hit a point where this thing is no longer be able to conduct, and I'll see it on my ammeter where it's going to have current, and then all of a sudden, boom, the current is going to go and drop away. It's probably the better method of testing. And that being said, chances of you field testing an SCR until you get into a lot of chemical work or into a lot of DC work is going to be slim to none, that you're going to be using this a lot. Know how to do it. Know that you do have to go and have a positive on your anode, a negative on your cathode, but don't rely on trying to run it through your multimeter. It's just probably not going to work. Okay, that's the end of our learning task 3. We will move on to number 4.